thank you for the introduction, and thanks to the organizers, and especially to the technical team for making it so smooth. So I'm going to basically continue on what Peter started, and also what Georg started talking yesterday, and try to discuss with you the prospects for many-body physics with ion atom systems. And on the way, I'm going to mention collaborations with a lot of fantastic people without whom I wouldn't be able to stand here. So on the theory side, much of the work has been done by Grisha Straharczyk, Luis Peña-Ardilla, Richard Schmidt, Antonio Negretti, and my student Baldo Cavazos. On the few-body physics, I collaborate with the local group of Michał Tomsa and my student Piotr. And on the quantum simulation side, which I will just very briefly mention with Joao, my student, and Antonio Negretti. And here you see a representative picture of the most handsome of these physicists. And here I have an even more handsome group of people from the fantastic experimental groups, which in this case I will restrict to the Freiburg team led by Tobias Schetz and the Stuttgart team of Tilman Pfau and Florian Meinert. So first, there has been a lot has been said about atom-ion potentials, and from the point of view of a prospective many-body theory, what we need to take into account is this tail of the interaction, which is power law with the fourth power in contrast to the van der Waals interaction, which from the point of view of scattering theory is actually a short-range potential. There is nothing very special about it. It has a scattering length, an effective range. So in principle, if you imagine collision theory, there will be modifications to the threshold laws, but it's all cosmetics, essentially. There is a Langevin rate which is independent of energy. We can easily take this into account. But from the many-body perspective, what is crucial is that this range of the potential, the characteristic range, is much, much longer than for the neutral atoms. And the energy corresponding to this characteristic range is much, much smaller on the other hand. So this roughly corresponds to the height of the P-wave potential barrier. And because it's typically much smaller than a microkelvin, it means that it's much harder to reach the S-wave limit in atom-ion systems. So kind of fortunately, all the chemistry at few-body inelastic processes and couplings, they happen at much shorter ranges than R star, where the electron overlap becomes important. And in this region, the potential well is very deep, and typically large energies are involved compared to the trap scales. So even if you are not able to cool the ion to very, very low temperatures comparable with the surrounding gas, you have sort of an energy scale separation, and you can work in a Paul trap and study exciting few-body physics. And there are lots of impressive experiments. Some of them have been shown over the past few days. There is a problem, of course, with reaching the S-wave limit, but if you want to study some chemical reactions, this is not crucial. Of course, it's crucial if you want to check the threshold laws, as Johannes Dagmar was showing yesterday. And one of the benchmark experiments, and from my point of view, a great achievement on the way to do many-body physics, was the observation of atom-ion Feshbach resonances. So Feshbach resonances are a generic mechanism of a coupling of a bound state in the closed channel to your open channel. And the physics of Feshbach resonances is relatively simple if you know well enough the interaction potentials. And it turns out in the system in which it was demonstrated, the barium-lithium, this physics is not exactly simple, but it's manageable, and we can more or less understand the structure. For other systems in which you can neglect the spin-orbit coupling, the dominating resonances come from the frame transformation between the molecular and asymptotic basis, and you can deal with it theoretically in a pretty efficient way. There was a poster of my student 2 days ago on a sample formulation of this scattering problem. And of course, Tom has shown us the beautiful experiment they did in which they identified a lot of resonances, much more than the simple theory could predict, as Agata mentioned, so I will not elaborate on that. But what this shows is a promise that we can go to the S-wave limit, because now if we enhance the atom-ion interaction by a Feshbach resonance, the sympathetic cooling protocols will be much more efficient, they will work much faster. So it seems there is a hope to reach much lower temperatures. And this is really needed if you want to do many-body physics, because in contrast to the few-body processes, here if you want to couple to the gas of atoms, to the phonon structure, to these excitations, they are all on a much, lower energy scale. So you need to cool the ion down a lot. if you want to reach this. And there are exciting prospects, as Georg shown yesterday, for the polar ion physics with a little bit different features. Induced interactions, even if you trust the experimentalists that they can improve by still some orders of magnitude. And moreover, the charge of the ion is easy to control with electric field, as Tillman was showing as well. So there is a nice prospect for some transport measurements, hopefully in a strongly correlated gas with strong interactions, making connections to condensed matter physics. And even to build on that and extend the system to a lot of ions and try to do some quantum simulator with a lattice structure. And there was also a poster of my student about that. But we need to lower the energies of the ion, because the kinetic energy of the ion in a Paul trap is much higher than the phonon energies, and we need to have it under control. In particular, the micromotion-induced heating and the excess electric fields, they spoil the system from the point of view of many-body theory. So a good illustration of what one can be interested in from the many-body point of view is this ionic polaron, or the mesoscopic bound state. You can call it as you want, that Peter showed for one dimension. We are also interested in that, but we wanted to see what happens in 3 dimensions. And here the core of the effect is this competing length of the atom-ion interaction and the healing length of the gas in which the ion is immersed. So because the extent of the two-body bound state is competing with these typical interparticle distances and the healing length of the condensate, you cannot use a delta interaction potential. So the gas would need to be much, much more dilute for you to replace it with a delta interaction. So even though this is a shortage potential, it's not in this particular system if you plug experimentally relevant numbers. And what we turned to was Monte Carlo simulations based on the diffusion method done by Grisha Straharczyk. And with a model potential similar to the one that Georg shown yesterday with these B and C parameters, we showed that the ground state of the system, as you add particles to it, as a function of the number of particles, you add particles and they all occupy the bound state of the atom-ion potential, up to the point in which the boson-boson repulsion becomes too large. So they all sit in a close vicinity to the ion, as you see here, and at some point this interaction energy and the correlations between the bosons due to that interaction starts dominating, and the energy goes more or less flat. And this happens when you bind of the order of 100 atoms to the ion. So this is not captured well by the mean field theory, of course, and also this particular state one cannot retrieve by making Bogoliubov approximations and dressing an ion with a phonon cloud. So here you can see this many-body bound state, or a mesoscopic molecular ion composed of 50 atoms. And then as you add more atoms, they do not bind, and instead they create a background gas in which this object is moving. So here the ion is mobile. And we tried to extend it to the case of 2 ions. It seemed interesting to us. So now the numerics needs to be simplified more, and we consider static ions. We do not allow them to move. We just place them at some distance to each other and try to calculate the ground state of the system and the energy of this state as a function of the ion separation. We choose the potential both here and on the previous slide to have only one two-body bound state, because we are looking for the ground state. So if we allowed a very deep potential, well, the system would just collapse to these deep bound states. And we can tune the scattering length of the potential and see what are the effects. Here you see a very, very weakly interacting potentials okay, it's not very weakly interacting, but it doesn't have a bound state at all. So there is no state to which you could bind the atoms. So you don't expect a cluster to be formed. And indeed, if you look at the density profile of the single polaron, it's pretty flat with a slight increase where the potential well becomes deep. And the energy of the system as a function of the separation roughly sits at the energy of a single polaron or of a single many-body bound state, and then it decreases slightly as you move the ions closer together. You can see that this decrease becomes observable for very, very short separations, actually of the order of 1 or 2 R star, which is experimentally not very reasonable number. And then we can tune that scattering length of the potential to other values or introduce a bound state and see how the physics changes. So here you have the unitary limit. It's a threshold at which a bound state appears from above and the scattering length diverges. And here you see that the energy scale changed, and now this binding of two ions is much stronger. And moreover, it has a weird shape here, which one wouldn't expect from it's just not very intuitive. And it's well explained by this huge bump in the atom-ion correlation function due to the existence of this bound state on the threshold, which tends to move atoms towards the ion and creates a very large density increase. And this inhomogeneity in density is visible also in the shape of this induced potential that we see. And now if you introduce a bound state, the physics is very much dominated by the presence of this bound state. A lot of atoms populated and the energy scale changes yet again. And this effect of the of the kink in this induced interaction becomes even stronger. One could see it also on the density profiles of the gas. Here are the integrated density profiles in one dimension along the ion separations. Here you can see a single density profile for one ion. And here, if you put two ions basically on top of each other, and you see that the density of this object doesn't really correspond to two ionic polarons sitting on top of each other, but instead there is this huge induced interaction which is attractive and leads to bump in this density and the feature being much narrower. If you separate two ions very well, then the density profile just resembles two separated objects. And in this intermediate case, you see deviations from these separated polarons start being visible. So there are reasonably strong interactions of the order of even hundreds of E star for two separated ions. And you can see some more details in this paper that appeared on the archive on Wednesday. So we are interested in trying to explain these features, but with a simpler answer, because these Monte Carlo calculations are quite costly. So we try to improve the mean field theory, but make it include this inhomogeneity in density around the ion. In a way, it's similar to the gross ansatz that was mentioned by Peter. You do a variational ansatz for the wave function of the bosons, and you get a modified Gross-Pitayevsky equation as basically rediscovered by Schmidt and Enz, or extended by Schmidt and Enz, and also Pietro Massignan at some point for neutral polarons. So for the ion, the preliminary results that Ubaldo Cavazos got, you can see the increase in density around the ion, which can be translated into an effective interaction between the atoms and the ion, being slightly more repulsive than the actual two-body interaction. And this stabilizes the polaron. So it stabilizes the gas from collapsing onto the ion, this slight repulsion that is induced. And then you can study the standard quantities like the number of atoms bound to the cloud. Here it's put in some arbitrary theoretical units, but it depends on the parameters of the potential. So this is an ongoing work, and I hope we'll get more results soon to show you. So this is all interesting, and these are features which you do not expect in neutral impurities because of the separation of length scales in a system of bosons with a spin impurity, for example. But the question is how to access it and how to measure now the transport properties. And now I turn to my favorite experiment, which was improved considerably, as Tillman showed you, and done in Stuttgart, in which they do not use a Paul trap. They aim to create an ion directly from a Rydberg excitation and then ionize it with well-controlled electric field pulse, and then let it float in the BEC and drag it with an electric field. So doing a classic transport measurement, but now in an ultra-cold setting and with an ion. And then the ion can be extracted and detected with a microchannel plate. And we can study the time of arrival at this microchannel plate, and from this infer how many collisions happened in the gas, and hopefully also some more features. So in this experiment, I think now it can be done with much better precision with the microscope that Tillman showed yesterday. But in this demonstration of the interaction of the ion with the buff, it was enough to simulate the physics with a semi-classical model in which the ion undergoes free ballistic motion dragged by electric field, and at some point it happens that it collides with an atom, and we can draw the probability knowing the atomic density in the cloud. And then if it collides, we know that the collision is governed by the Langevin rate. We can draw the scattering angle from the differential cross-section because we know well the ion energy. And then we update and keep track of where are the gas particles, in which place in the cloud the ion now is, what is the density around it, and what is its velocity. And from this type of model, you can extract, for example, the stationary state of the ion if the condensate was large enough for this stationary state to be established. And from this drift stationary velocity, one can get the ion mobility, which is the basic parameter in the diffusion and transport theory. So here are some results that were obtained. You can see the ion trajectory or the ion time of arrival as a function of the time that it was let to spend in the condensate, and the numerical simulation that is in reasonable agreement with the results, with basically 0 fit parameters, just based on a very precise knowledge that they got about their density profile and the structure of stray electric fields in the trap. They were able to almost reproduce it without fit parameters. And as a function of the field, you get now that you can extract from these the drift velocity, both in the experiment and simulation, and the mobility of the ion is a slope of these two curves. So you can see they are in the same order of magnitude or in qualitative agreement, which for me was a surprise actually that these curves are not completely off, and it means that even at this stage before building the microscope and mapping the stray fields with a very high precision, they already had an impressive accuracy. So without free parameters, you get the mobility of the ion. It's, from my point of view, it's impressive, but from the point of view of many-body quantum theory, it's just a classical particle bumping off gas particles and moving through the gas. And that's because the ion energy and the time that it's allowed to spend in a condensate are still do not allow for matching to the many-body quantum physics. So we would need to let it stay in the condensate at much lower energy, so it doesn't really move, that it's mobile, but it's not dragged through the gas. And then maybe we could see some increase in the effective mass because of the buildup of correlations around the ion. But with the new technologies, I think it's only a matter of time that we see an effect like that. So with this, I want to continue to the holy grail of ion-atom many-body systems. So unfortunately, it's a bad news. I would advise to get rid of the Paul trap and switch to other systems. So either create a free low-energy ion or transfer it to an optical trap. And this optical trap, actually, the shallower the better. So we need the ion to have a really low energy, and we need the trapping potential to not perturb its motion locally, so that we can apply the same approximations as we do for trapped ultra-cold gases, that the potential locally doesn't disturb the motion. Then we expect that the lifetime of the ion would then be limited by the free body loss, which could potentially kill the whole experiment and prevent us from seeing the polarons. But this free body loss typically can be controlled to some extent by the gas density and by the interaction strength, by the Feshbach resonance. So there are prospects for finding a sweet spot like that. And then ideally we would like to image the ion, both the ion and the gas, to see when the ion arrived at the detector and from where it was excited, and what were the correlation functions in the gas at that point, to get the full picture of the many-body state that is created. Ideally outside of equilibrium, of course, so to probe some transport dynamics. And this is a problem which is studied for a very long time, since the 1930s, since the beginning of quantum mechanics, but still we have not that many results on that. And in such a controlled system, I think it's a perfect test bed for this type of measurement. And the questions are really basic, like is an ion in a gas a well-defined quasi-particle with an effective mass, or does it create a bound state with zero particle residue? This is like one of the basic questions that could be answered in such a system. So in conclusion, I think a lot of other speakers shown that ion atom systems are now approaching the quantum regime. There is really amazing progress in experiments, much beyond what the theorists imagined 10 years ago. But the requirements for doing many-body physics in an experimental setup are extremely, the demands are extremely high. But as the experimentalists keep surprising me, I have high hopes that this is still a promising field. And the polar analytic physics of an ion in a gas is exciting, especially if it's out of equilibrium, or if you introduce more than one ion and try to bunch them at a short separation. So this is my current group, and I would like to thank you for your attention.
Great, thank you very much. Questions?
Regarding this GP equation you showed at some point you're working on right now, is that the same approach as Pietro did with Chris Pethick a long time ago, where he put an ion in a, is it like a static ion and then you solve for the
No,
GP
the ion is mobile, so you do, it's what Pietro also wrote in a more recent paper. At some point, you do a Lilo-Pines transformation and you get a modified Gross-Pitarevsky equation.
Yes. Mass instead.
Yes, basically.
Okay. And it's one or two ions you solve for what?
No, now it's one, but it can be extended to an arbitrary number, I think. It's not a big problem.
Tillman?
Thank you for the nice talk. You mentioned the three-body recombination might be a limit in the end for the many-body physics. And you were sort of optimistic that you can choose parameters to avoid this limitation. Maybe you can say a few more words about this, because I mean we have a long range of that interaction always, right? And you said you can use Feshbach resonances or so, but Feshbach resonances, to my knowledge, always increase the three-body rate.
Yeah, the Feshbach resonance.
So
if
maybe
you sit at a resonance, it increases the losses. But if you turn outside, then the minimum of the losses happens it is displaced with respect to the zero interaction. So the zero crossing of Feshbach resonance usually does not correspond to the minimum of the free body losses exactly. And I'm just hoping, based on the neutral atoms results, when this free body recombination is a problem, but it is under control, let's say, for a lot of experiments, there is no fundamental difference here because of the long range of the potential. So there are calculations being done right now on the speed of the free body recombination, the rates, and I think we will not see any disastrous numbers with respect to neutral atom case.
Okay. Any last questions?
Thanks for the nice talk, Krzysztof. So one question regarding your outlook, where you said that ideally you would like an experiment to be able to track the motion of the ions and also the position of the atoms to trace out the correlations. So it is quite challenging, I think. But would it not be possible to, do some kind of non-spatially resolved measurement, because if there is really correlated motion, then that should kind of reflect in the vibrational frequency of the ion. That would be much, much easier to measure. But at the same time, you also said that you don't like a trap, so maybe you can elaborate on that.
Yeah, I don't like the trap here. I mean, almost no theorists like the trap in this particular problem. But I think you don't have to restrict to spatially resolved measurements. You can go to momentum space with the gas. You can measure some spectral response. That's all. That all helps, I guess. So I do not expect you to reproduce the snapshots from the Monte Carlo calculations. That would be not necessary.
Thank you.
All right, let's thank Krzysztof again.